Hi friends, welcome to GMK tutorials. In this video we are going to see about the power gating concept. It is also a very important concept in the leakage power reduction point of view. So in the last couple of videos we discussed regarding what is meant by VTC mass and what are the advantages as well as limitations in the VTC mass, as well as in the preceding classes also we discussed about the MTC mass, multiple threshold CMOS circuits, implementation criteria, and what are the different threshold voltages are we are using in the MTC mass point of view, and what is the drawback as well as what is the advantage of MTC mass. Now the same MTC mass concept can be extended to the another name that is generally called as power management or power gating. It is a very important concept. So here in this power gating point of view, in case of this basic strategy, it consisting of two modes generally. That is nothing but one active mode, and second one is nothing but low power mode. So active mode means that it is a normal mode of operation. Low power mode means that it is like a sleep mode in case of the previous techniques. So let us see here the active mode, which is a normal mode of operation of the circuit. Low power mode means that when the circuit is not used. Simply we know that the circuit is not in use means that we can also call as this mode is generally called as a standby mode, right? It is also called as a standby mode. Okay, as well as the low power mode is commonly referred as we can also call it a sleep mode. Okay, it is also called as a sleep mode, right? So as well as the basic power management means that obviously it is very important, right? Let us see here. The management means that if you are thinking anything, the work should be perfect on time, right? So let us see in this case, and at an appropriate time, the circuit switches from one mode to the another mode in appropriate manner, such that the energy drawn from the power source is battery is also very less, as well as that means the impact on the corresponding performance is also very less. That is a basic thing here, right? So this is the overview of this slide. Next, move on to the next one. So now we have to see what is the difference between clock gating versus power gating. Generally, you know that clock gating means whenever if you need your circuit is a clock supply, at that time only we are providing a clock signal to the corresponding circuit. That concept is generally called as clock gating. So within the clock gating point of view, just we can reduce the leakage power in the standby mode with somewhat lower compared to the previous version as well as previous generation, right? So the power gating is also same concept that can be used to give the power supply to the corresponding blocks or maybe circuits with the help of some external switches. The switches also we can call as a sleep transistor. It may be PMOS transistor or it may be NMOS transistor. So based on that concept, we are providing the power rails or maybe VDD as well as ground to the corresponding internal block. That may be that block consisting of maybe inverter or whatever it may be. So that is a basic thing overview of the corresponding power gate. So let us see here. In the previous generations of the CMOS circuits about 250 nanometers range, the leakage power is insignificant. That is a very important point. So that's why I can mention highlighted that key point also. That means at that time we don't want to bother about the leakage power, because of that leakage power is very negligible compared to the dynamic power dissipation as well as total power dissipation. That's why we don't want to think about that one also. But if you go for the technologies goes on increasing nowadays, therefore the overall generation technologies increases, we can design the circuits with a less number of very least size, that is nothing but around 90 nanometers range or maybe 70 nanometers range. This leakage power is very important parameter. So that's why we have to reduce that leakage current. Otherwise, it draws the maximum energy from the battery. Therefore, it leads to the battery life is also decreased. That is a very important thing. So for that purpose, we are using the gate concept. So let us see here. However, the leakage power has grown from leakage from every generation of CMOS technology, and it is essential to use the power gating to reduce the leakage current. As well as the power gating can be implemented, The power gating can be implemented by inserting the power gating transistors in the stack between the logic transistor or either power or ground. So that is what we discussed in the few seconds later. So that is the basic concept of the power gating. So let us see The logic block contains a all high VT consisting of generally, if you observed in the previous case also, in case of empty CMOS point of view, we are using inverter, right? We are using one inverter. On the top of that one, we are using a 2 sleep transistors. So that is the basic thing. So here also same thing. So for the fastest switching operation, the switches may be transistors or headers or maybe photons using with the high VT transistor to minimize the leakage. So the basic concept overall in case of the power gating is nothing but you have to use the two types of threshold voltages. One is nothing but low VT transistor for fastest speed of operation, as well as lowest or maybe high VT transistors are used for minimizing the leakage current. That is a very important thing. As well as these power gating reducer techniques. The power gating reduced by gate to source voltage, because the gate to source voltage is the minimum voltage that is required to form the channel between the corresponding source and drain. So that is voltage is also called as, we can call it as threshold voltage. So which can drive the logic transistor deep into the cutoff region. So based on that gate to source voltage only, whether the transistor is going to be work in the cutoff region, or it may be saturation region, or it may be active region. So when the transistor is going to be in the cutoff region means obviously the circuit is in a high transistor mode. When the device in the high transistor mode means obviously which reduces the leakage current. Therefore overall power dissipation is also decreases. That is the basic concept. Okay. So that is the summary of this complete slide, right? Okay, let's move on to the next one. So let us see the difference between the, it is very important diagram. So the first one shows that how the clock gating is used in the previous section. So let us see, generally the power, this shows the power, this shows the time axis here. So the power, total power is equal to, this is the sum of dynamic power as well as it is a leakage power. But if you are using the clock gated concept, obviously that leakage power is decreased to somewhat, maybe some level actually. Still, if you are using the same activity profile for the subsystem with a clock gating as well as activity profile of the subsystem with a, so therefore the overall power dissipation, there is nothing but leakage current range in case of the clock gating network. Suppose if you are using the clock gating concept to the corresponding same circuits, obviously we can reduce the leakage current from this level to the very small level. Compared to this one, this is our previous level, this is a difference of the range of the corresponding leakage current is decreases by using the power gated circuit. So the main theme behind this power gate concept is nothing but just you have to we are not providing any kind of the power to the corresponding circuit. Therefore what happens is that the circuit is working the standby mode. Okay, at that time the leakage current is reduced by the high VT transistor. Therefore leakage current is reduces means overall power is leakage power is also reduces. That is the basic concept behind the power gated concept as well as leakage. As well as in case of the clock gated means that we are providing the just a clock signal is stopping, but we are not switch off the power supply rails as well as to the corresponding supply voltage to the circuit. Just we are stop the clock signal only. So therefore internally whatever the power dissipation provided by the internal components, it may not be stopped at the clock gating circuit point of view, but we are think very deeper into the corresponding circuits point of view. Then we have to think about, okay, if you are reducing the supply voltage, obviously if you are stopping the power supply to the corresponding circuit, obviously the device is not function. Therefore obviously it is in the standby mode, or it is also called as a cutoff mode. Therefore high VT transistors act as a on condition. Therefore it reduces the leakage current. That is the basic theme behind the power gating concept. Okay, then so the power gating issues, these are the some of the power gating issues. If you are using any technology, obviously some of the drawbacks is also associated with that technology. Let us see one by one. Generally, let us see. So the clock gating approach is discussed earlier does not affect the functionality of the circuit. That means the clock gating cannot affect the overall functionality, because of we are not changing any kind of the circuit operations within the circuit, right? So that's why we don't have any bother about the internal functionality of the circuit. As well as if you want to change that is based on the RTL designer only, we'll take care about that when we are applying the clock signal, when we are stop the clock signal. As well as it affects the interblock interference as well as significant time delays in order to enter the exit power modes. That means we have to think about the when we are going to on the corresponding device when we are going to supply the corresponding signal, as well as the most basic form of the power gating control and the one with the lowest long-term leakage power is extremely switched power supply. So because of the switching power supply is also one of the reason for that one also. So it is also having some issues, that is nothing but these are the issues: power gating granularity, topology, switching fabric design, isolation strategy, retention strategy, power gating controlling design. These are all the internal part of the corresponding power gating issues. Let us see one by one what is happening. So here let us see, the first one is nothing but power gating granularity. So in case of the power gating granularity, what it is consisting of two types of methods, that is nothing but fine grained, and second one is nothing but coarse grained. Fine grained method means in case of the fine grained method, the power gating to the switch is placed locally as a part of the standard cell. That means if you are considering any standard cell, within the standard cell fits only we can design the cell. That is the basic thing about the, so the power gating circuit is placed within the locally as a part of the standard cell. So that is the basic thing. So within the part of the cell only we are providing the signal, as well as the switch must be designed supply the worst case current requirement of the cell, so that no impact on the performance. That means this switch produces a very worst case condition, that means very less amount of current. Therefore obviously what happens is, that means that if you are providing the less amount of current means that obviously no leakage power will be there, as well as it is obviously we can maintain the performance is also no effect. But as a consequence, the size of the switch is usually 2 to 4 size of the original cell. Because of if you are using the internal cell means with the switch is placed inside the cell, what happens is that the size of the device is also increases. So the size of the device is also increases. So that means there is a significant overlay or area it is increases. So the whatever it is nothing but fine grained operation means that simply you have to remember one thing: the switch is placed within the cell. Let us see, just I will explain in a blank slide. So if it is, let us consider it is a switch is like this switch. So the switch is placed within the this is nothing but overall switch. This part is nothing but cell. That means the switch is placed inside the cell. This is generally called as a fine grained granularity. So the drawback is nothing but if the switch is placed internally means that obviously the area is also increases. That is the overhead problem in case of the fine grained concept. Okay. So fine grained power gating is to reduce the runtime leakage power, that is the leakage power consumed during the normal operation. One of the best advantage of the fine grained means that basically up to now we are thinking about the standby mode reduction of the leakage current only. But this fine grained gating is to reduce the runtime leakage current. Not only in the standby mode, in the runtime mode also some leakage current is produced. That leakage power can be reduced with the help of a fine grained. Okay, so that's why in the normal mode of operation it reduces the leakage current. As well as coarse means that we can also call this, it's like a simply it is a maximum size. That means in this case more than one switches are connected in a similar fashion to provide a virtual VDD as well as virtual ground to the corresponding circuit. That is the best simplest way to remember the corresponding course. So in this case, let us see the power gating relatively a large block, say processor or maybe block of gate is the power switched by a block of switch cell. Moreover, this coarse grained example mentioned above will reduce the leakage current in the standby mode. Actually, the fine grained is used to reduce the leakage current in the dynamic mode, or maybe it is also called as a normal mode of operation. But the coarse component is used only in the standby mode. So that is also somewhat limitation. Moreover, the switching operation of the coarse grained is not up to the mark because of more number of switches are functioning at a time, because of internal delays is also there. So that's why the switching is not possible all time at on time only. One more drawback is nothing but the coarse grained concept is only used for a large block of cells only. It is not used for a single block, because of if you are using for the single block concept, obviously more number of switches means that area penalty is also increases. Okay, then the choice of the granularity, that means this fine, whether you are going to select the fine grained or coarse grained, it completely depends on the two parameters, that is nothing but logical, and second one is nothing but physical implementation. The power domain refers to a group of logic with a logically unique sleep signal. Power domain means a group of logic with a locally unique signal. That is also very important. Each power domain must be physically arranged to share the virtual ground common to the particular core. So if you are using the power domain concept, means that we are providing some virtual VDD to the corresponding block by sharing the corresponding same signal. That is also very important. Another advantage of the fine grained power gating is that timing impacts current, as well as the current I passing through the switch with a equivalent resistance of R. The resulting IR drop across the switch can be easily characterized by the possible to use the traditional design flow to deploy the fine grading concept. That means if this current is passing through the corresponding circuit with some resistance, we can estimate the corresponding current. So what kind of the current is going to be flow, and how we are going to reduce the corresponding leakage current. That kind of the analysis is very easy in case of the fine grain. On the other hand, the coarse grained switching networking is more difficult because of exact switching activity of the logic block may not be known at the designing time. So that is one more problem. In spite of the advantages of the fine grained power gating, the coarse grained power gating is preferred because of the lesser area overhead. In spite of the advantages of fine grained power gating, the coarse grained power gating is preferred because of its lesser overhead. That is also one more advantage. Coming to the power gating topologies point of view, we have three types of topologies. That is nothing but global, second one is nothing but local, and third one is nothing but switching cell. So let us see one by one. Global power gating, the name itself represents global clock gating. Generally you know that global clock means that a single clock that is used to share for all the devices within the parts of the circuit, right? So here also same thing. So let us see in this circuit diagram here. So here this is nothing but one switch. So the switches are connected in a parallel fashion. So all the switches drains are connected to one part of the one common signal, as well as sleep signal is also applied to all the signals at a time. So here the block 1, block 2, block 3 means the block may be any kind of the device, whether it may be inverter or maybe any functional block. We don't want to think about that. So this circuit is act as a virtual ground to the corresponding block 1, block 2, block 3. That means a common signal is act as a virtual ground for the all the blocks. That is nothing but global means that a single source or single wire is act as a, so that means this common signal is act as a virtual ground for the block 1 as well as block 2 and block 3. That means these three blocks share only single signal. That means if you are using any single signal within the complete circuit, generally called as a global signal. Here also same thing. So global power gating refers to a logical topology in which multiple switches are connected to one or more blocks of a logic, and a single virtual ground is shared in a common among all the same thing. Right? This topology is effective for large blocks. That means it is very useful for the large blocks only. That means it is not used for a single block. If you are using for a single block, means that obviously the area penalty is also increases. So that's why we don't want to prefer global power gating for the single switches, as well as it does not apply when there are many different power gated blocks which are controlled with different sleep enablers. So it is just used for common point of view. Okay, so that is a basic thing. Second one, local power gating. Local means that simply it is a individual. So local power gating refers to it is one kind of a logical topology in which is also same thing. Switch is singularly gates its own virtual ground. That means each and every block having its individual switch. So the corresponding individual switch provides as a virtual VDD, virtual ground. So this provides a virtual ground. So that means here each and every block maintains its own switch. That own switch provides a corresponding power rails to the corresponding circuit only, right? So that is the basic thing. Next one, switch and cell. The name itself represents switch and cell. Switch and cell means that within the switch, within the cell, within the switch, this switch cell is nothing but a maximum switch. switch in cell. That means if you are considering this complete part is a cell, within the cell a switch is placed. So this box represents as a switch. Within the cell a switch is placed. So that's why we can call it a switch within the cell. So that's why it is called the switch within the cell. So here switch in cell may be a thought of an extreme form of a local power gating. In this topology, each logic cell contains its own switch. So the switches cannot be provided by the external side. The switch may be existing within the cell itself only. So that's why called as a switch in cell. But the drawback is nothing but if you are placing the corresponding switch within the cell means that obviously size is increases. Yes or no? So that means if you are placing the switch within the cell means that the cell size is also increases. Cell size is increases means that area increases. If the area is increases, obviously different issues will be there. So that is just one kind of the limitation in case of the switch in cell, right? Next, move on to the next one. So switch fabric design. So switching fabric design means generally up to now we have preferred how to use the different switches. That means how to use the switches in the local, global as well as switching cells. Then how can you design the corresponding very effective method for placing the switches, whether the switches are placed in the header or footer like that. Obviously we have to think about where we are placing the switches. So for that purpose this concept is very helpful. Generally switching fabric design consisting of the two methods. Okay, so first and foremost among the issues are architectural issues to decide whether the switch only header switch using a PMOS transistor or use footer switch using an NMOS transistor. That means it is also very important actually. So if you are placing a switch on the top of the corresponding circuit or maybe bottom of the circuit, we are think about the what happens. So architectural issues are the one example. Okay, as well as some researchers have advocated that use both styles of switches. However, for the design at 90 nanometers or small 90 nanometers, that means maybe some of the researchers said that only single switch is enough for operation, but some of the researchers told that better to use two kinds of the switches. That may be better for the operation also. So let's say either the header switch or footer switch is recommended due to the tight voltage margin and significant IR drop and larger area and delay penalties when both types of transistors are used. So this is also one way of version. That means if you are using a different two transistors means that obviously two switches means that area is increases. That is also another issue. So various issues to be addressed for the switching fabric design. That is nothing but one by one we will discuss. One is nothing but header switch versus footer switch on power gating implementation technology. So how to choose the corresponding switches. So what is meant by header switch? Header versus footer switch. The name itself represents header. Header means the top obviously in case of the word file and all those things. So that means the switch is placed on the top of the logic block, top of the logic block. That is generally called as a So here the switch is placed on the top of the logic block. So that's why it is called as a header switch. Okay, here the switch is placed on the bottom of the corresponding logic block. Therefore, we can call it a footer switch. So the header switch is nothing but obviously always the header switches are act as a high VT transistor. That means the transistor threshold voltage is always high. As well as the footer switches threshold voltage is nothing but low VT transistors. Okay, we know that why we are providing the high VT as well as low VT. Importance already discussed in the previous slide. As well as the key issue affecting the choice are architectural constraint. That means by using the corresponding header and switches, obviously what happens that the area is also increases, IR drop constraints are somewhat important. The header switch is also suitable for if multiple power rails or the voltage sinks are used in the switch. So the header switch is also useful for different application. As well as if you are using any switch, switching active is also very important. That is also decides how the device is operated, how fast it is operating. So switching efficiency is nothing but we can defining here. It is a ratio of on time by half time, that is generally called the switching efficiency. The maximum value of switching efficiency is desirable to achieve the high current drive in the normal mode operation under low leakage in the normal condition. That is also very important. As well as if you are using the header switch using a PMOS transistor, results in 2.6 times more leakage current than the footer switches realizing using a NMOS transistor. Okay, these are some of the statistics in the given by the some papers, right? So these are the some implementation styles. That means how we are going to implement the corresponding switches, and obviously it can be performed with the help of a two styles. One is nothing but ring type, and second one is nothing but a grid type. So the name itself ring type means that, let us see here, these are the two styles. So here all the switches are connected to the VVD, that is nothing but virtual VVD in a particular fashion. It's like a one kind of ring fashion. That's why it is called a ring style. Second version is nothing but a grid style. Grid style means that obviously it is nothing but a one kind of the box. Grid is generally called it in a boxes format, right? So that's why it is connected in this fashion. It's like a row wise fashion. That's why it is called a grid style. So here also this is nothing but VDD. This is act as a virtual VDD. So it is also act as a virtual VDD. It is also act as a virtual VDD. This is a fashion of connecting the corresponding switches in some particular fashion. Based on the fashion of the corresponding switches are connected, we can call it is a ring type. It may be called as a grid type, right? So that is the basic thing, right? So in the ring tile implementation, switches are placed external to the power gated block by a encapsulating by its ring style, as well as switch is connected to the VDD as well as virtual of the power gated block. So these are all discussed in the previous slide, right? So isolation strategy. What is meant by isolation strategy? Isolation strategy means that, let us see here very quickly, this complete overall theory can be explained here. So let us see here, this is the output of the power gated block driving the power up block. Suppose generally if you are taking this voltage, this voltage may be completed, may not be reaches to the high VDD point of view, as well as it may be cannot be decreased to the complete zero. At that time, this whatever the voltage across this voltage is switches. This voltage is act as a driving for both PMOS as well as NMOS. That means these two switches may be on condition due to the corresponding voltage. So that leads to the short circuit in the corresponding driving circuit. That is a basic drawback actually. So for that purpose, you have to maintain this voltage. You have to shift this voltage to the whether it is a high VDD or it may be completely zero voltage. Then only we can on the any one of the switch in the inverter case. That is the basic property. So that can be represented here. Ideally, the outputs of the internal nodes of the header style collapse down towards the ground. Similarly, the outputs and the internal nodes of the photo style power gated block also collapse down towards the supply rail. However, that means in practice, outputs and the internal nodes of the neither discharge to the ground nor to the fully recharged. So that is a basic problem. That means it may be completely discharging to zero as well as it cannot be charged fully to the VDD also. That is why it is a one kind of the drawback actually. So for that purpose, due to that problem, it may be on the corresponding two devices. So for that purpose, you have to provide only one voltage. That voltage is suitable for driving the second voltage. So this complete analysis also, for that purpose I have to use one sleep transistor here. So that is also there in the power gated block. So let us see here. So the output of the gate is corresponding gate is connected to the So here the thing is that the output is also connected here. The sleep transistor output is also connected. So it can be raised to the 0 or 1. So based on this one, the AND gate produces whether it is a high voltage or maybe low voltage. So if it is provided low voltage, that voltage is suitable for on the corresponding PMOS transistor only. Obviously NMOS transistor is going to be half condition. So that's why now we can maintain that value to the whether it is a 0 or maybe 1. Basically it is a, let us see, it is a 3 types actually. This isolation can be achieved by using the isolation cell to clamp the output of the power down block to the some well-defined logic. That means that well-defined logic is suitable for operating the next device. As well as the isolation cells can be categorized into 3 types actually. That is nothing but cells those clamp the output to the 0 level, logic level, as well as cells that clamp the output to the logic 1. That means it produces a 0, 1, as well as it produces some most recent value. Most recent value. So these are the 3 outputs of the isolation cells. So based on this one, we can produce it. So to which the value of the output should be clamped based on the interactive state of the power block. As well as in case of the active high logic, the output is clamped to the 0, active low logic, the output is clamped to logic 1. So these are the scenarios. So that means whatever the gate, this gate produces a logic value, whether it is a 0 or maybe 1. So that means obviously the intermediate value can be raised to maybe completely 0 value, or maybe it may be 1 value. So that's why these circuits are generally called as a clamper circuit. We don't want to prefer based on the circuit operation, we can prefer these are the different types of the gates we are using in case of the clamping point of view. So this is also called as AND gate is used for clamping low. So these are clamped high. So these are the, obviously there is another question mark is also there. That means if you are inserting these kind of the gates, AND gate and OR gate, these AND OR gates also having some propagation delay. If you are using such a kind of the devices within the propagation, within the critical path, obviously the overall delay of the critical path is also increases. So that is also one of the consequence of the corresponding placing the AND gate and OR gate in between the power gated circuit as well as a non-power gated circuit. So for that purpose you have to prefer such a kind of the transistor, that is nothing but PMOS and NMOS transistors. Slip transistor can be used for the clamping the corresponding output, whether to the high value or maybe low value. So that is nothing but just a brief introduction, right? So this is nothing but a state retention strategy. In this case, given a power switch fabric and isolation strategy is used, with the help of those two techniques, we can design a good method to resume the operation of the power on block. Must be either have a state recorded from the external source, and we build up a state from the reset condition. So that means state retention means that we are getting the previous value. That is a general meaning, right? The retention means that maintaining the previous value, or we are taking the corresponding previous value. So let us see here. It is of a three types actually. So this is a software approach. It is based on the reading and writing operation of the register. The second method is nothing but scan based approach. It is also based on the reuse of scan chains of store state on chip. Third one is nothing but register based approach. These are the three strategies we are using. Software based approach means that within the software we are writing some part of the code. That part of the code is used to design the corresponding values are going to be stored in somewhere else. After completion of the power gating operation, we are taking the same values from the corresponding CPU. That is the basic operation. So let us see one by one. In the software approach, always on CPU reads the registers of the power gated block and stores in the processor memory. Okay. As well as during the power up sequences, the CPU writes back the registers from the memory. But a traffic shows down the power down and power up sequence. Bus conflicts may be power down during the unviable, as well as software must be written integrated into the system software for handling the power down and power up. So the basic thing is nothing but that means the CPU is that take care about the corresponding operation. So CPU reads the information of the corresponding register when the device is going to be power off situation. Whenever it finds the device is in power down, at that time the CPU get back the corresponding data from the memory. That means the data is stored in the corresponding memory, processor memory. After whenever the device is getting the power gated signal, at that time the same information whatever it is stored in the memory, that can be retrieved from the memory, that can be placed in the registers. So this all operation can be performed based on only software only. So that's why it is called the software based approach. So it may be part of the operating system, or maybe separate drivers may be preferred to perform the switching operation. So that is the internal issues. Okay. Next thing, scan based approach. Scan based means that a scan chains are used. That means a built-in self test can be reused. That means during the power down sequence, a scan registers outputs are routed to an on-chip or off-chip memory in such a so here also same thing. Whatever the data is placed in the register, when the device is going to be in a power off situation, the information is going to be stored in the on-chip memory. Whenever the device is going to be on condition, at the time the same data can be reloaded to the corresponding register. That is the basic approach of scan based. Coming to the retention based, here we are using some kind of the registers. So the retention register can be shadows. That means it is a completely like let us see here. So this is this is also like a master slave operation. So this is a master, this is nothing but a slave actually. So the master, when the device is going to be a powered off situation, at the time the master gives the information to the slave to store the corresponding information. When the device is going to be power on condition, at the time the same information is given to the master. So initially the master gives the information to the corresponding RET device at the time to store the corresponding value. As well as if the device is going to be non-condition, at that time it takes the data from the corresponding devices also. So this is also a overall operation of the corresponding devices. Okay. So this is all about the retention register point of view. So it's like a master slave operation, the JK flip flop. So thank you for watching GMK tutorials. Thank you. If you want to more videos, so please subscribe our channel as well as share your friends also. So thank you. Thanks a lot.